Potential due to point charges. Now that I've introduced the concept of electric potential, let's look at the electric potential energy and the electric potential between 2 point charges. Imagine that I've placed a positive charge q at some point in space which we'll call the origin in our coordinate system. Now suppose I have a test charge q sub 0 that I can move from, say, along the x-axis from point A to B or from B to A. We'll assume that q sub 0 is the one that's moving and this charge is fixed. Now as I move q sub 0 towards q, remember that these two charges are like, I would have to apply a force in the opposite direction to bring these charges together. And hence I would have to do work to increase the potential energy of this system. It's kind of like as if there was like a spring between these two charges and I were trying to compress the spring and bringing this charge closer and closer to charge Q. So as I physically move this test charge from point B to point A, it's like I have to push it up the hill in order to get it closer to this charge Q. And hence the electric potential energy will increase. What would be the work done in moving this charge from point B to point A? Now you recall that work equals force times displacement, but you can't simply just multiply the force at B and then times the displacement, because as you push this charge closer and closer and closer to point A, the force gets stronger and stronger and stronger due to Coulomb's law. If you recall, Coulomb's law is F equals kq times q sub 0 divided by the distance squared between the two charges. And hence, as you bring the charges closer and r gets smaller, the force will get bigger. So really the only way to calculate the work done is to use some integral calculus. And so the work done for moving the charge from point B to point A would be equivalent to the area under this curve. Using calculus, we'll end up with this result. So the work done in moving the charge between A and B would be equal to kq times q0 all over RA, this distance, minus kq q0 divided by the distance r sub B between these two charges. The work done in moving from point B to point A through this external force applied in the opposite direction of the electrostatic force would cause an increase in electric potential energy. And so these two terms are really electrostatic potential energy terms. You see, the first term is the electrostatic potential energy of the system when this test charge is located at A and this is fixed here. And the second term, the energy here, represents the energy of the system when this charge is still fixed in this location, but now the test charge is located at point B. So really, each of these terms just simply represent the electrostatic potential energy. So you'll see written down here the electric potential energy of a two-charge system, Q1 and Q2, at a distance of r apart from one another is given by this expression. On the AP formula sheet, it is written this way. Note that this is the energy of the system. It's not just the energy of, say, Q1 or just Q2. It's the energy of the two-charge system. You also note that this equation is very similar to Coulomb's law, except there's just an r on the bottom here in the denominator, whereas the Coulomb's law equation has an r squared. So be careful not to mix this up. I often see people do that on the exam, mixing up a force with electric potential energy because the equations are very similar. But there is just an r here, whereas in Coulomb's law you have an r squared. Also, I should mention that when you look at a two-charge system, as the distance r increases, so as you move Q2 further and further and further away, as r approaches infinity, what happens to the potential energy of the system? Well, as r approaches infinity, the potential energy of that two-charge system will approach zero. So the electric potential energy of a system is defined to be zero at infinity. Another way to look at it is to think of it this way. Imagine I place this single Q1 charge at this empty space. I'd have to do no work to place it right there. Now, imagine I have some charge Q2, way far away, off this screen out to infinity, and I were to drag this charge Q2. and move it all the way closer to this point in the proximity of Q1, right at this point P at a distance of r. The work that I would have to do in moving that charge from out to infinity to this point P would be really equal to the electrostatic potential energy K Q1 Q2 over R. If Q1 and Q2 are both positive or both negative, I would do then positive work in creating this two-charge system. However, if one charge was negative and the other charge was positive, then the product of these two charges would have a negative potential energy, and so hence the work in moving charge Q2 from infinity to point P here would be actually a negative work done. So it's important to realize that when you're using this equation that you need to keep the signs with Q1 and Q2 so that you end up with a positive or a negative potential energy, or zero potential energy if R is at infinity. And also, the work done in moving this charge Q to this point P is independent of the path. I could take a very complicated, crooked path to get to that location, and the same amount of work would be done. I don't have to go in a straight line along the x-axis to get to this point P, because electrical forces, just like gravitational forces, are conservative forces, and it really doesn't matter what path that you take. Just think of it like lifting a book from up a meter. It really doesn't matter what path that you take to go from A to B. As long as you have that same change in height, you have the same change in potential energy. So the work done, or the potential energy in moving a charge, is path independent. Now let's introduce the concept of electric potential at a point P from a charge Q. So let's say we have at this empty space here, we have this charge capital Q. Located at a position P, we're going to put a test charge Q, little q. We'll call it positive, but it could be negative, it really doesn't matter. And we also have the distance between this charge Q and this location at point P, we'll just call that R. We learned earlier that the electrostatic potential energy of this system can be calculated by using K times Q little 0 divided by R, the distance between the two charges. This energy represents the amount of work to move this charge way out from infinity all the way to this location point P. The electrostatic potential, V, is the amount of work done per unit charge, the charge that we're moving. And the work is equal to the electric potential energy of the system when it's at this location R divided by Q0 now. And then substituting our electrostatic potential energy into the equation, and you will see that little test charge Q sub 0 cancels out. And so we get the electrostatic potential is equal to K times Q divided by R. The SI units of this term of electric potential is in joules per coulomb, which we name the volt, named after Alessandro Volta. So therefore, the electrostatic potential at a point P at a distance r away is given by this formula. We'll just call that a capital Q because that's what we used in our picture. And note that you can have positive, negative, or zero potential. If you have a negative Q, you'll have negative potential, which means you had to do negative work in moving that test charge over to here. And also, just like electrostatic potential energy, when R approaches infinity, the electrostatic potential is 0. Alright, the next thing you need to know as well is how to find the total potential energy, or the total electric potential of a system with more than, say, 2 charged particles. First, let's look at this example here. You have Q1, Q2, and Q3, 3 charges here. If we were to ask to calculate the total electric potential energy of this system, we'll call that U, it would be the algebraic sum of all the different pairs of charges. So for this configuration, we would have to calculate the potential for each set of pairs of charges. You can think of it like this. Imagine you have Q1 that we've just placed in this empty space. Then we bring Q2 from infinity to a fixed location. The work done in moving that charge Q2 to this location would be this first term. And then finally bringing Q3 from infinity over to this location here, the work done would result in these two terms. So when you have to calculate the potential energy of a system with more than two charged particles, like this picture here, you need to calculate the potential energy for every pair of charges, and then add all the terms algebraically. In a similar way, you can calculate the total electric potential for two or more charges. The total electric potential is the sum of the electric potential for charges Q1, Q2, Q3, etc. at distances of R1, R2, R3, etc. So, for example, if you were to try to find the electric potential at point A, you would have to use KQ1 over R1, that's this distance, plus KQ2 over R2, which is this distance, and KQ3 over R3, which is this distance here. And the beauty about electric potential energy and electric potential is they're all scalars, and so you don't have to worry about vectors at all. But remember, you do need to put the signs of the charges. Sometimes you may end up with a negative answer, and some terms will obviously be negative, like this term here. If you were to find the electric potential at point A for this entire system, and then find the electric potential for another point B for this same system, then if we take the difference between the total potential at A minus the total potential at point B, we end up with what's called the potential difference, and we call that the voltage. Now you should be ready to try practicing by doing example number 2.